Hi, we are Group 8. Our topic is Smart Road Monitoring System. I am Gan Jianyong, and my teammates are Hitako, Liu Tianpei, and also Ting Weishen. For the background of Smart Road Monitoring, first we need to know that Smart Road is a route or highway that utilize the advanced technologies such as speed sensors, acoustic sensors, IP CCTV cameras, smart traffic lights, and so on. So Smart Road Monitoring includes the collection and analysis of data in real time. For manual route monitoring, it is a traditional way of the route monitoring includes the visual inspection of routes by trained personnel. In this slide, I will introduce the comparison between smart route monitoring and also the manual route monitoring. For smart route monitoring, it is easily to be understood that it uses a range of sensors and communication networks to collect and analyze the real-time data on traffic flow and also route conditions. Humans may make mistakes more easily compared to devices when we apply the manual route monitoring, which may lead to the incorrect management towards the result. Therefore, it can show that the smart route monitoring is more efficient, accurate, and also safer. In the terms of the cost effectiveness, the smart route technology is a one-time investment that requires minimal maintenance, whereas the manual monitoring requires ongoing personal costs and can be expensive over the long term. In the terms of the valuable insights, smart monitoring can provide valuable insights into the traffic patterns and also the route conditions, which can help transportation authorities to make an informed decision about route infrastructure and traffic management strategies. In this slide, I will introduce the history of smart route monitoring. In the early 1990s, the first intelligent transportation system (ITS) was introduced in the US. In the late 1990s, a consortium of the government agencies, research institutions, and also private companies in Japan launched a project to develop a smart highway system. In the early 2000s, the European Union launched a series of initiatives to promote the development of smart roads and also the intelligent transportation system. In the middle 2000s, the development of smart road technology began to accelerate, driven in part by the advance in the communication networks and also the data analytics. In recent years, the development of smart road technology has continued to accelerate, driven in part by the increasing availability of connected and autonomous vehicles, 5G communication networks, and also other factors.
Greeting Miss or Sir, my name is Sitaho. I will be presenting a future trend of a smart road monitoring, problem statement, and objective and the proposed solution. There are several future trends of smart road monitoring. I will introduce two of them. First, we may anticipating a rise in the usage of cutting-edge sensors that can gather more information about the traffic flow, road conditions, and other elements that influence traffic safety. The road infrastructure will incorporate these sensors, allowing for real-time monitoring and decision-making. This will boost road safety, improve traffic flow, and lessen congestion. Second, in order to optimize the traffic flow and risk safety, smart road monitoring system will need to be able to communicate with the autonomous vehicles as they proliferate. To ensure that this system can function in a unison, new technologies and standards will need to be developed. Next, I will talk about the problem statement of this topic. The issues of maintaining effective and safe roadway is what smart road monitoring for pothole and obstruction identification attempts to solve. Roadblocks and potholes can lead to the catastrophic accidents and damage to the automobiles, which can be quite expensive for both drivers and the communities. In order to detect and pinpoint road hazard, smart road monitoring system for pothole and obstacle identification use cutting-edge sensors and machine learning algorithms. These systems are capable for detecting potholes, debris, and other road hazards with great speed and accuracy. The objective of this project is to develop a system that makes use of existing cloud provider that can help to detect the pothole and obstruction on the highway road to prevent accidents. In this project, we will make use of Amazon Web Service (AWS) as a platform to provide a system that helps to detect whether there's a pothole or any other obstruction on the highway road. This system will use the radar, sensor, and camera as the tools used for the pothole and obstruction detection. That's all for my part. Thank you.
Good afternoon to my friends. My name is Liu Tianpei and now I'm going to present about the proposed solution in our project. As we can see, this is the architecture diagram of our project, and in this architecture diagram, there are two modules that we done in this project, which are the root obstruction detection and the pothole detection. And now I'm going to explain all the components and how it flows inside our project. So the first component which we used was AWS IoT Core. AWS IoT Core is a managed cloud service that provides connectivity between IoT devices and the cloud. Based on the figure at the side, we first connected our device IoT, which are the camera and the radar, to AWS IoT Core. The second component is AWS Lambda. There are 4 lambda in this architecture diagram, which the first lambda will trigger to store the images from IoT Core to S3. After the images were stored in the S3, the second lambda will be triggered, which the AWS recognition will recognize the image. If the obstruction or pothole was detected, the lambda will be triggered again, sending an email notification to the root department using the SNS service. The third component is Amazon S3. In our project, we store the image capture in the S3 bucket system. The data in the bucket can be accessed globally to other services. The fourth component is Amazon Recognition. Amazon Recognition is a machine learning service, and it can analyze the images without the need of building a machine learning model. We use this service to analyze the captured image. The fifth component is Amazon SNS. It is a publish and subscribe method as a messaging service. Users need to subscribe to the topic in order to receive a notification when there is an obstruction or pothole detected. The sixth component is Amazon DynamoDB. This is a non-structured database using NoSQL. In the pothole detection module, the result data will be stored in the DynamoDB. The seventh component is Amazon Kinesis. There are 2 components that we use in this project, which are the Amazon Kinesis data streams and the Amazon Data Firehose. Amazon Kinesis data stream was used to process streaming data retrieved from the IoT core, and Amazon Kinesis data Firehose was used to load the streaming data into the data store, such as the S3. The eighth component is Amazon Athena. It is an interactive query service, allowing users to analyze data in S3 without the need for complex infrastructure. In this project, we get the data from the S3 and analyze using the Amazon Athena. And the last component is Amazon QuickSight. After the result was analyzed, it will pass us to the Amazon QuickSight to do the visualization of the result. That's all from me. I will pass it to my groupmate to continue his presentation. Thank you.
My name is Ding Wei Sheng. Now I will present the study of different IoT platforms. First, device connectivity and management. This includes AWS IoT Core, AWS IoT Hub, Google Cloud IoT Core. For the edge computing, there are AWS IoT Greengrass, Azure IoT Edge, and Google Cloud IoT Edge. All provide a way to perform local processing of IoT data on edge device, enabling faster response time, lower latency, and offline support. Next, analytic and insight. AWS IoT Analytic, Azure Stream Analytic, and Google Cloud Data Flow are all cloud-based analytic services that enable processing and analysis of streaming data from IoT device. Last, machine learning. AWS IoT offers several machine learning services for IoT application, including Amazon SageMaker, which enable training and deploying machine learning models on the IoT device. Azure IoT Edge also provides support for Azure machine learning, while Google Cloud IoT Core integrates with Google Cloud Machine Learning Service. That's all for me. Thank you.
So now I'm going to demo on the root obstruction detection, which is this part. So firstly, we need to go to the AWS IoT Core, and in the MQTT test client, we need to subscribe to this topic, which is the Smart Root Camera Test. And then we go to the Visual Studio Code, and this is the code where we connected to the IoT devices, which is the camera. As here we can see, the image file was read, and we encode the image into the base64. And then we subscribe to the topic just now, and we publish the image to the topic. So when we run the code, we can see the camera was connecting to the AWS IoT core. And we go back to the AWS IoT core, we can see this is the base64 code image. And when we go to the S3, we refresh it, and we can see the image was uploaded. This is because the lambda function was triggered, which we will first read the image, and we will decode the base64 image back to the JPEG image, and then we will call the S3 bucket, and we will upload the image to this obstruction image, which is the bucket name. So when the image is successfully saved in the S3 bucket, it will trigger another lambda function, which is the recognition lambda. So basically, this is where we call the AWS recognition to recognize the image. When the recognition recognizes, which is the 3, and the confidence is above 50, then it will send an email. It will send an email notification to the root department email. So when we check our email, we can see that the email was successfully sent to us, which we can see the obstruction is detected on the root, and what is the object, obstruction, and the confidence.
Now I'm going to demonstrate the root obstruction and pothole detection part. So initially, in a vehicle, we have a radar sensor and also a GPS. So the radar sensor will read the time reflection from the vehicle to the route and back to the vehicle, while the GPS will read the current locations coordinates. When these two data is being published to the AWS IoT core, then it will through the AWS Lambda to trigger the Amazon SNS and also the Amazon DynamoDB service. In AWS IoT MQTT test client, we already subscribe to this topic, which is a device /plus/ data. And then in the SNS, we need to clarify that we make an assumption that the normal distance between a vehicle to the route is 30. So any reflect time that more than 30, we assume that there must be detected that there is a pothole. Now I'm going to show how this works. In this code, visit command, there is some variables that can be changed, such as the number of the device and the total number of message to be published, and also the content of the message. As shown, there is a message being published. So we can check in the MQTT. After that, because that this reflect time is more than 30, which means that it should be detected that there is a pothole. So we can check in the email. Initially, there is no email. After we refresh it, it should have a AWS notification message. Show that there is a possible pothole with a reflect time of how many, and also the location. Then in the DynamoDB, after we refresh the page, it should have data.
Now I'm going to demo the model, which is a real-time streaming of data. So basically, after the data is published at the IoT core service here, it will trigger the Amazon Kinesis data stream. This Kinesis data stream will collect the data. After that, it will process and analyze the data. After that, it will trigger the Amazon Kinesis data firehose here. This Kinesis data firehose will allows you to capture and deliver the streaming data to the other services such as the Amazon S3. So for my case, it will deliver the data here to the Amazon S3 and the AWS Glue. Okay, as you can see here, this is a AWS IoT core service here. So at the MQTT test client here, you can publish the data here. After publishing the data, you can go to the Amazon Kinesis service here, click on the data streams tab here. After that, you can click on the data stream you created just now, and then at the monitoring tab here, you can see the statistics of the guide records here, as you can see here. This indicates that your data stream got the record successfully. After that, you also can click on the delivery stream tab here, and then click on into the delivery stream you created just now. Also at the monitoring tab here, you can see the statistics of the records read, which indicates that your delivery stream successfully got the records and able to read the records here. Okay, now go to the Amazon S3, click into the buckets tab here, and then find the bucket you created just now to receive the data, and then click into the file. It will take some time, so wait for the data to be received by the buckets. If you still didn't get the data, try to refresh. And as you can see here, this is the data which is published from the IoT core services just now. It successfully delivered from the Amazon Kinesis firehose to the Amazon S3 bucket here.
Now I will present the demo of Athena and QuickSight and launch query editor. Then we need to select the database we need, and then we enter the query that we need and then run. So the query is run completed. We will see the result that we can use in the QuickSight and click the QuickSight. We go to the dataset and use the new dataset and then select and then create. Select the table. After that, we select a table and we can throw the value inside. So it will help us to generate the table. So we adjust more, and then we can use the conditional formatting. I add the background color for the value that larger than 30. Yeah, this is the result. And then we can share and publish dashboard. Now we can see the dashboard. That's all for me. Thank you.